Hello all, welcome to video tutorial on how to design, simulate and implement FFT using MATLAB and Xilink's Vivado design suite. Before getting into design, recommendation for audience, it is necessary to have basic knowledge on how to use Xilink's Vivado design suite, MATLAB system generator toolset, digital signal processing concepts, DSP theory, and Simulink. With the assumption that audience have all above mentioned knowledge, let's get started for working with MATLAB system generator and exporting designed IPs to Vivado. It is recommended to configure Xilink's Vivado design suite and MATLAB. To know more about MATLAB and Xilink's Vivado version compatibility, search Google for MATLAB version compatibility with Vivado you are using. For tutorial purpose, MATLAB R2018A and Xilink's Vivado 2019.1 versions are used. Before starting design, it is recommended if MATLAB and Xilink's Vivado are configure. To check if Vivado and MATLAB are configure, launch System Generator 2019.1 MATLAB Configurator by clicking on it. If MATLAB and Vivado is already configured, tool shows configured. If not configured, click on Find MATLAB and check the box next to Version on MATLAB and click on Configure and click OK. Now both tools are configured, we are good to start using System Generator. To start with, click on Start, and launch System Generator 2019.1. Do not launch MATLAB directly from Start menu. System Generator will launch MATLAB and load all the necessary files required to generate and verify DSP designs on FPGAs. MATLAB loads based on the speed and memory of your host PC. MATLAB will have four main sections: current folder to the left of the screen, editor window to the center top and command window to the center bottom, and the workspace to the right. Copy or download the file by the name fft_design.zip. Make a new folder, give a name of your choice and copy the file into the folder. Extract file. On extracting you'll get two files with the extension m-file, which is related to MATLAB script file, and another with extension .slx, which is Simulink file. Copy the file path, and point the file path in working directory. Double-click on VIB_sensor_spec_m.m file to open MATLAB script. Script defines sampling frequency of ADC, sampling time for Simulink block sets and Hanning coefficient. Run the script by clicking Run button or by pressing F5 on keyboard. Here sampling frequency, fs, is taken as 200K as incoming ADC data is sampled at 200K SPS. Fs is then multiplied by factor of 4 because to facilitate overlapping of ADC samples. For understanding purpose, overlapping of ADC samples means, for every 50K SPS of new ADC data 150K SPS of previous ADC samples are attached so that FFT can be interpreted in more efficient manner. Memory defining overlapping of ADC samples requires clock which is 4 times more than that of sampling clock. Hence the maximum sampling time is defined as 200K multiplied by 4 equals 800K. For which the entire FFT system works at 800 kHz. All other clocks are derived using 800K clock as reference. Since in this design we are using downsampler block which downsamples ADC sampling to 10K SPS, division factor 20, all derived clocks need to be multiplied by factor of 80 and 20 wherever applicable. Since all the parameters are set, let's start by launching Simulink tool by double-clicking VIB_sensor.slx file from the current folder. Wait till the Simulink loads. Simulink tool loads the pre-designed block design containing Xilink's block sets and DSP blocks. In the current design, we have 5 important blocks, namely Decimation block, Memory block, Overlap, and Hanning window, FFT core, and, most importantly, Xilink's system generator tool itself. Each block will be explained in detail. It is highly recommended to study UG 897 Vivado Design Suite User Guide for detailed insight on how to use model-based DSP design using System Generator. This model must include system-generated token. It defines how the model needs to be compiled into hardware. First step in the flow is to open System Generator token by double-clicking on it. Under Compilation dialog box, select board type to None, Part, ZYNQXC7Z0472FFG900, Compilation. IP catalog. Select the appropriate directory for output files, and leave all other parameters as defaults. Under Clocking dialog box, enter 10 nanosecond under FPGA clock period. Enter T under Simulink system period, sec, and leave all other parameter as empty and click OK. Let's start with the decimation block. In this module, ADC samples, which is sampled at 200 kSPS, is taken as input through ADC_data_in at 200 kSPS sample time and buffered into next stage. As ADC code is bipolar in nature, and FFT IP requires data to be in between -1 to +1. Incoming samples are subtracted by 32,768 and reinterpreted to -1 to +1 by placing binary point at 15th position of 16-bit ADC. For debug purpose, reinterpreted signal is taken out output to top module. Next stage in signal flow comes FIR filter. Place the block and type num in coefficient vector space and leave rest settings default. Click OK. To generated coefficient for FIR filter block, place FDA tool block into design. FDA tool is configured as low-pass filter to have passband 4.5 kHz and f-stop at 5 kHz with order 800. Generate coefficient by going to File, Export, check Overwrite Variable, leave Rest Default, click Export. For debug purpose, FIR output is taken as output to top module. Next stage in design will be downsampling to 10 kSPS. This sample rate is achieved by downsampling incoming sample 200 kSPS by factor of 20 to get 10 kSPS samples by selecting last value of frame. For debug purpose, downsample output is taken as output to top module. For rest of the design flow, downsampled data will be used for processing. Next block in the design is memory. This block is responsible for generating memory address and trigger signals which will be used in storage of down-sampled ADC data and overlapping of ADC data. Count_1 generates address for write cycle of overlapping dual-port RAM memory, RAM_WR_ of depth 4096. With each increment of address, down-sampled ADC samples is stored to dual-port RAM address in incremented every t into 80 seconds, that is 100 microseconds. Add_1 adds count_1 with const_2 constant block with 1024, which will be used for overlapping logic implementations. Comp is used to compare count_2 has completed one full Hanning read cycle and signals FFT_t. Last, which indicates that last data is processed, which is an input for FFT core. Count_2 generates address for Hanning coefficient stored in ROM, Han_R. D_address, address band from 0 to 4095. With each increment of address, ROM outputs Hanning coefficient, which will be used to multiply with overlapped ADC samples. Address is incremented every t into 20 second, that is 25 microseconds. Count_3 generates address for read cycle of overlapping dual-port RAM memory, RAM_R. D_address of depth 4096. This is loadable counter with the initial value of 1024. Initial offset of 1024 is used because of overlapping of ADC samples. For better understanding of overlapping of ADC samples, dual port memory is used, which has 2 port. Same memory space can be used for read cycle while write cycle is writing to. 75% overlapping is done for more efficient validation of ADC samples, meaning for every 1024 new ADC samples 3072 samples of previous data is attached. Hence making 1024 new samples plus 3072 old samples making 4096 sample frame, which is multiplied by Hanning coefficient and processed by FFT core. To explain memory structure, let's divide dual port memory in 4 equal block of 1024 depth. While write cycle takes 102.4 milliseconds for one write cycle to block 1. Read cycle makes 1 cycle to acquire 4096 samples at 25 microseconds each, that is, 25 microseconds into 4096 equals 102.4 milliseconds. Since read cycle has initial offset of 1024, assume one complete write cycle is completed on dual port memory, block 1 to block 4. Write cycle is writing to 0th location dual port memory. Read cycle starts from 1025 location, goes up to 4095 and rolls back to 0. By this time read cycle has acquired 3072 samples from memory, and the time take to complete this activity will be 76.8 milliseconds. At this time write cycle will be writing to 768th location. Read cycle starts reading from 0th location and write cycle writes from 769th location. At the end of write will finish writing to 1023 location and read cycle completes reading 1023 location. In the next cycle, write cycle starts from 1024 location and read cycle starts from 2048 location. By doing so 75% of previous ADC samples are overlapped with 25% of new ADC samples. Next block in the design is overlap_Han window. This blocks consist of dual port RAM, DPRAM, for 16-bit width and 4096 depth. A read-only memory, ROM, which holds Hanning coefficients, which is generated from MATLAB. Define depth as 4096 and point to initial value vector as window_coef and select block RAM as memory type. A multiplier, which multiplies overlapped ADC samples with Hanning coefficient, which will be used by FFT core for processing. Next step in the design will be configuring Xilinx FFT Core 9.1 version IP. Xilinx provides proven, resource-optimized and configurable FFT Core in its DSP toolkit. For this project FFT Core version 9.1 is used. For more information on IP Core, it is highly recommended to study PG 109 for IP usage, I/O configuration, register configuration, test bench, etc. Based on the document study, FFT IP core IOs are configured with the constants values. To configure FFT IP, double-click on FFT core. Set transform length to desired length. In our case it is set to 4096 point. Target clock frequency to 1 MHz. Architecture choice as pipeline streaming I/O. Under Advanced tab, set 16 as phase factor width in precision options. Select unscaled under scaling option. Select convergent rounding under rounding modes. Output order as natural order. select xk_index under optional output fields. Under Implementation tab, set 7 under number of stages using block RAM. Under Optimized options, select Use 3 multiplier structure as complex multipliers and use extreme DSP slices for butterfly arithmetic. FFT core outputs processed ADC data onto real and imaginary output port. FFT core also output bin index, which will be used to locate frequency component and to extract frequency information. Chordic core IP is used to extract magnitude and phase information from the processed FFT data. This is the final stage of FFT design. All outputs are tuned to have same delay, so that all data arrives at the output port at same time. All outputs are taken to top module for further process and interpretation. At this stage, all necessary configuration to IPs and blocks are made and design is ready to be verified. All necessary connection and configuration are done. Now it's time to verify design for its functionality. To simulate the design, let's set input to known frequency, say 1 kHz. Connect scope to output ports of the design. For deeper understanding, right-click on the canvas to select Xilink's waveform viewer to tap signals in Vivado viewer environment. Select the signal that you want to tap, right-click on it and add to viewer. Once done with selecting all signals, on top of the canvas, set simulation stop time to 1 second, and click Run. Allow tool to build the project, and double-click on Scope to open Scope Viewer. Wait till simulation has completed. Once simulation is done, open Scope to view if signals are captured properly. Click on Autoscale X and Y axis. The first window displays magnitude output, second window displays FFT last data arrived signal. Third window displays input data to FFT core, ADC multiplied with Hanning coefficients. Fourth window displays frequency bin index. Any window can be zoomed by using Zoom tool. Open Xilink's waveform viewer, and zoom into the FFT peak. Index corresponding to peak represents the frequency set as the input. To calculate frequency from the bin index, let's find bin resolution. Bin resolution equals sample rate, 10 kHz, divided by FFT point, 4096, which gives 2.4414 Hz per bin. Hence 410 multiplied by 2.4414 gives close to 1000 Hz. Now design is verified. Let's package the design that can be used as IP in Vivado block design. Double tap on Xilink system generator token. Verify the target directory where IP need to generated. Click on Generate to create and package design. Wait till IP is generated. Click OK once IP is generated. Open folder where IP is generated. Double-click on IP subfolder. Verify that folder contains all necessary IP design files are present. We have designed, simulated and exported FFT design. This ends the FFT design part in MATLAB Simulink tool. By this we end part 1 of video tutorial. In part 2 we will learn how to import exported IP in Vivado and build system around it. Thank you.